The next chapter I'm going to present together with Thomas, so let's get into the heart of things. And the topic is assessment of the right ventricle.
Okay, so now the question is, how do we actually quantify pulmonary hypertension? Andreas, how would you go about?
Well, actually, in everyday clinical practice, we use an integrative approach using different measurements of pulmonary hypertension. First of all, certainly tricuspid regurgitation and a CV Doppler signal to get an idea about systolic pulmonary arterial pressure, and it's certainly the most widely used parameter quantifying pulmonary hypertension. But never forget that there are additional signs in your echo study that you can use for quantifying and assessing pulmonary hypertension. And as you can appreciate on the patient on the left, that there is quite severe right ventricular hypertrophy. And have a look at the thick myocardium there. The last finding that I wanted to show you is the flattening of the interventricular septum.
So I think it's very important what Andreas has said, that there are more than one parameters that we can use to assess pulmonary hypertension. And in general, Andy, what should we use?
Well, I think actually we should use an integrative approach.
But still, we should actually always start with tricuspid regurgitation.
And that actually makes sense because it's present in more than 75% of normal adult population. And if you have a look in your patients and you look for it specifically, I think you'll get even a high percentage of patients where you can actually find tricuspid regurgitation.
And actually, sometimes you have the impression it's always a matter of how good you can image. The better your image quality is and the better you are able to image patients, the more likely it is you will find tricuspid regurgitation. And it's also a matter of how good the machine is. Sometimes I actually use the ability to detect tricuspid regurgitation to determine if a machine is good or not. But now let us focus on how to quantify TR velocity.
And the first thing that we have to do is align our CV Doppler with the tricuspid regurgitation jet in order to get a proper signal that we can use for measuring it. But we're not going to talk about that theoretically. Have a look at the video.
Now we'll take a look at how to perform a continuous wave Doppler to measure pulmonary pressure in a 62-year-old patient with pulmonary hypertension. So we perform the measurement from an apical view. The first important thing that you have to remember is that you always have to get a good 2D image. If you don't get a good 2D image, you will not get a good color image. The next thing you will have to use is the color, which is used as a reference. So once you have the color, what you try to visualize is the proximal portion of the jet, the vena contracta, because you have to put the continuous wave Doppler through the vena contracta. So again, we'll use the color as guidance, and then we'll use the continuous wave Doppler signal, and we put the focus point right at the portion where the jet originates. So I'll just show you what happens if I move the focus point away. You will see that I will lose the signal. If I go back into the region, all of a sudden the quality of the Doppler signal increases. So this is a Doppler signal which is very easy actually to get. We can measure the maximum velocity, which is somewhere around 5 meters, which means that the patient has a pulmonary pressure which is far above 100 millimeters mercury. But this is not always as easy as it is in this patient. Sometimes what you have to do is you have to rotate the transducer and look at the right ventricle more from a two-chamber view, and thereby you can also visualize eccentric jets and thereby get a better orientation between the continuous wave Doppler and the regurgitant jet, which should always be parallel. Let's try this again. So this would be a velocity again around 5 meters. And finally, if you do not get a good signal from the apical view, I would recommend that you move up one intercostal space. And if you move up one space, sometimes you also get a better jet, not in this case, and sometimes higher velocities. And finally, you also have the possibility to perform a right parasternal long axis view. and measure the tricuspid velocity there. Not in this case, but especially in cases where you have a jet which is directed more towards the posterior portion of the right atrium.
Normal values for TR velocity range between 1.7 and 2.3, and ideally you should take age, sex and body mass into consideration because that influences the velocity as well, especially age.
Now here are 4 different spectrums of 4 different patients, and can you immediately recognize what the difference between these spectrums is?
Well, certainly if you have a look at the scale on the right hand side, then you can appreciate that there are different severities of pulmonary hypertension indicated by different velocities of the TR. But there's more to it.
Take a look at first of all the density of the TR signal. Here you can see a signal which is not very dense. Now that can be indicative of not so severe tricuspid regurgitation, but it can also be due to poor alignment. Here in the bottom we see that the TR velocity varies from beat to beat. Now this is caused by arrhythmia. And then here we see a patient who has a more rounded shape of tricuspid regurgitation, while the shape of the TR signal is more pointed in this patient. Andreas, why do you think this is the case?
Well, that's not only due to TR severity, but also to right ventricular function. Both influence the shape of the TR signal. So to summarize, there is a number of factors influencing the TR signal. That's first of all the severity of TR, pulmonary hypertension, the angle of the TR jet to the CV Doppler signal, and of course image quality, and don't forget right ventricular function.
But very important, keep in mind that patients who have pulmonary hypertension do not necessarily have to have severe tricuspid regurgitation. And vice versa, if someone has severe tricuspid regurgitation, it does not mean that he has severe pulmonary hypertension.
So at the first glance, detecting pulmonary hypertension simply by using TR velocity seems to be easy. Unfortunately, there is no definite cutoff point. The higher you take the level, the more specific you are, but you lose sensitivity.
In general, however, I would say a cutoff value of somewhere in the range of 2.8 to 3.0 meters per second can be used.
But don't forget, TR velocity increases with age, so take higher cutoff values in the elderly.
But does elevated TR velocity always mean you have pulmonary hypertension?
Not necessarily. Here we have 2 examples. Both patients have high TR velocities. Can you see why? Well, in the patient on the left, you can see a huge mass compressing the right ventricular outflow tract. And in the patient on the right, you can see that there is flow turbulence across the pulmonic valve, indicating pulmonic valve stenosis. So Thomas, can you explain to us why we have high TR velocities without pulmonary hypertension in these patients?
Well, normally we have free communication between the pulmonary artery and the right ventricle during systole. Therefore, we have the same pressure in the right ventricle as we have in the pulmonary artery. If we have an additional gradient between the right ventricle and the pulmonary artery, then the gradient we calculate between the right ventricle and the right atrium does not correspond anymore to the pulmonary artery pressure. The pulmonary artery pressure will obviously be lower. And this was exactly the case in the 2 examples you saw previously. One patient had obstruction in the RVOT, and the other patient had valvular stenosis of the pulmonary valve.
But that's not the end of the story. So how do we get systolic pulmonary arterial pressure out of TR velocity?
Okay, Andreas, now it's time that you explain this formula to us.
Well, Thomas, I think you're kidding. It's been a long time that I've passed my A-levels, so I'm not going to resit them. In principle, this is the famous Bernoulli equation, and this considers a number of factors, such as convective acceleration, flow acceleration, and viscous friction. But fortunately, for us echocardiographers, we can simplify it. Have a look at the bottom line.
The pressure gradient is equal to 4 times the velocity squared. This is the most important formula you will find in echocardiography, and we will need the formula in many instances, not only to quantify pulmonary hypertension.
So all you have to do is take your peak TR velocity, square it, multiply it by 4, and add it to your right arterial pressure.
Can you give us an example?
Well, here we've got a patient who has almost 4 meters TR velocity. So if we take that and square it, then we'll get 16. And if we multiply that by 4, then we'll get 54. And that's our gradient. So what we have to do now is add the right arterial pressure, and then we'll get our systolic pulmonic arterial pressure.
But how do we get the right arterial pressure?
I don't know.
Well, how the heck do we know? But Andreas, I guess we have to be serious. Tell us, how would you estimate right atrial pressure?
Well, first of all, you can have a look at the jugular vein and get a clinical impression. Furthermore, you can go for the inferior vena cava, and tissue Doppler measurements over the tricuspid valve would be a good thing as well.
So, looking at these three methods, which would you choose?
Well, in everyday clinical practice, we mainly go for the inferior vena cava, and I think it's worth having a look at 2 examples. On the left, you can see a dilated inferior vena cava measuring 2.4 centimeters, and that's obviously abnormal. In comparison, on the right-hand side, you can see a patient with a normal inferior vena cava, and that's measuring 0.7 centimeters. And what we know out of literature is that this correlates quite well with right atrial pressure, and the cutoff value is around 1.5 centimeters.
But it's not only the width of the inferior vena cava, it's also the degree to which a vena cava collapses during inspiration. Now remember, if we inhale, we have elevated flow into the right atrium, and thereby we have collapse of the inferior vena cava. As a matter of fact, you see even more pronunciation of the collapse if you let the patient sniff. But take a look at the patient on the left. Here we have a complete collapse of the inferior vena cava, while on the right the vena cava only collapses approximately 50%. This too can be used to quantify right atrial pressure.
M-mode is quite helpful to visualize the collapse of the inferior vena cava, and you can see that nicely here on this picture. But be careful to keep the inferior vena cava centered, as otherwise you can produce a collapse where there is no collapse. Taking both parameters, the width and the reaction to inspiration together, you get a fairly good estimate about right atrial pressure. And you can see that in this table, which you can find in your fact sheet. So look whether the inferior vena cava is dilated and what happens if the patient inhales. But don't forget to have a look at the liver veins as well, because if they are dilated, that's a good sign for significantly raised right atrial pressure.
When you use the inferior vena cava, however, you have to be aware of a few things. First of all, there are some patients who have a wide vena cava even though they do not have elevated right atrial pressure. And then you cannot use it if patients are on mechanical ventilation. Another way to estimate right atrial pressure is by using tissue Doppler, a method we also use for the left atrial filling pressure. In principle, what we do is we look at the inflow signal across the tricuspid valve and at the motion of the tricuspid annulus. And by the formula you see down here, we can estimate the mean right atrial pressure. Now this is still very experimental, but it can be used in certain situations.
But it's also quite useful just to look at the right atrium in the 2D image. Have a look at this loop. You can see a bulging to the left. Tell me, what do you think? Is there another reason for this bulging?
Well, actually I know what the patient really has. This is a patient who has tricuspid valve endocarditis with a flailed tricuspid leaflet and significant tricuspid regurgitation. And if you take a look, you can see that the jet must be directed towards the interatrial septum, and that the reason for this massive bulging is probably also the jet which blows right into the interatrial septum.
We always want to classify into different severities, and when I had a look into literature, I was quite surprised that I couldn't find a definite answer to that. But what we use in everyday clinical practice is this scale. As doctors, we always want to classify severities, but when I went into literature, I was quite surprised that I couldn't find a definite answer. So what we use in everyday clinical practice is this scale. With mild pulmonary hypertension and a cutoff value of over 40 millimeters of mercury, moderate, cutoff value of over 50, and severe pulmonary hypertension with a cutoff value over 60 millimeters of mercury. But the question remains how accurate our SPAP measurements really are.
Well, I guess this is a very controversial issue, as a matter of fact, and there are a number of studies which show that it really correlates quite nicely with cat studies, but then there are studies which show just the opposite.
And one of the reasons for that is certainly the measuring of the signal itself.
Yes, I think this is completely true, and there are a number of pitfalls involved in measuring pulmonary artery pressure. But this will be the object and the topic of the second part of this chapter.
It's time for you now to take a short break.
But you can be sure, what does Schwarzenegger always say? We'll be back.